Hello, this is Mr. Stansbury. I'm going to take you through the notes on some attributes of polynomial functions. At the end of this, you should be able to say, I can sketch the graphs of cubic functions, identify end behavior of polynomial functions, and recognize even and odd functions. Okay, so first things first. Polynomial function is a function with whole number powers. And the degree of the polynomial function is its highest power. For example, let's say we have 3x to the fifth minus 2x squared minus x minus 7. The 5, this exponent of 5 is the highest power of any of these. It's 5, 2, 1, and 0. Since 5 is the highest number, that means it's a fifth degree polynomial. And the leading coefficient then, since this is our highest power, the leading coefficient would be 3. It's got a constant of -7 because it's got no x with it, and it has 1, 2, 3, 4 terms. Okay, this is a polynomial function, and it's got whole number powers: 5, 2, 1, and 0. Like, it wouldn't be a polynomial function if this was like 5 halves or 2/3, something like that. Okay. All right. Some of the common polynomial functions have specific names. So if it's a 0 degree, we call it a constant. So that -7 is a constant. 1 is linear. Plain old x is linear. Second is a quadratic. Third is a cubic, we call it. And fourth is a quartic, just so you know. Okay. A relative maximum is where the graph is at its highest point in an interval, and a relative minimum is where the graph is at its lowest point in an interval. Okay, so for example, on this one here, this here would be considered a relative max because it's the highest point in this area, even though it's not the highest point total in the graph because it gets higher and higher and higher over here. And then also over here, this would be a relative minimum because this goes down to a minimum point and then heads back up. It's the lowest point in this general area, but again, it's not the lowest point necessarily on the graph altogether. Okay. End behavior describes what happens to y, the y value, as x approaches -infinity and positive infinity. So maybe an easier way to look at that is to say, describe what happens to y as x is getting smaller and smaller and smaller. So like, say for this graph here, we can like say start at 0, and as x is getting smaller and smaller, which means going into the negatives. So as we're moving to the left, what's happening to all these y values? So we start at -4, -5, -6, -7, -8. This has got an arrow pointing down, so that means it goes down forever and ever. So that means that this would be going towards, y would be going towards -infinity. Okay, as x approaches infinity, so as x gets bigger and bigger, so it starts here at -4, it actually starts off by getting smaller and smaller, but as it keeps going and going and going, it's getting bigger and bigger and bigger. So that means as x approaches infinity, y approaches infinity in this case here. Okay, now this is a chart of a bunch of different powers. So we've got x squared, -x squared, x cubed, -x cubed, fourth, negative to the fourth, fifth, and negative to the fifth. Okay, so there's some actually some nice patterns that show up that can actually help figuring out some of this end behavior stuff a bit easier to understand. So what do each of the following all have in common? So what do all the positive polynomials here all have in common? Okay. So if you want to pause the video and like see what you can figure out, go ahead, and I'm going to tell you here in a second. But like all of these here, the big thing is, look, these both end up going towards positive infinity, both sides, positive and negative infinity. So do these, but these here don't. But here's the big thing that they all have is, look, if you look on the right side here, all of these end up going towards positive infinity. So all positive polynomials, as x approaches infinity, sorry, yeah, that's not a really pretty looking infinity sign. So as x approaches infinity, y will also always approach infinity. So it'll always end up going up. So all positive polynomials, functions, always end up by going up. Okay. Now all the negative polynomials, if you look at that, notice all of these end up going down. So on all negative polynomials, as x approaches infinity, y approaches negative infinity, because these all end up going down. Okay. Okay. All the odd-powered polynomials, so that would be cubes and fifth powers. So notice these. Look, these all are going opposite directions, right? So, so I guess the easiest way on this one would be end behavior is I don't know. I guess we'd go with like say opposite for both of these. Okay, so end behavior is opposite. And then on the even-powered polynomials, x squared, negative x squared, x to the fourth, negative x to the fourth, if you'll notice, the end behavior, wherever it's, like if it's going, these here are going towards positive infinity on both sides, and these are going towards negative infinity on both sides. So end behavior is the same. Is the same. Goodness sakes, that handwriting is terrible. Let me fix that. That at least looks a little better. Okay, we're going to look at some examples here, but first let's take a quick comedy break. Okay, let's take a peek at some examples here. It says use graphing technology to sketch a graph of the function, name the relative minimums and maximums, name any x or y intercepts, and describe the end behavior. That's a lot of stuff, but that's okay, we can do that. Okay, so get our handy dandy graphing calculator, turn that thing on, and really all we're going to do here is we're going to push the y equals, and we're going to enter this in just as it looks. Whenever you start with a negative, you got to push this negative sign down here instead of the subtraction sign. So we push this negative 2. Here's our variable is always right here, x, and this is to the third power. So we do up arrow, third power, and then you actually have to arrow over, otherwise it'll continue typing into that power spot there, which we don't want. Now, since we've got something in front, now we use subtraction. So we do x, and then it's squared. We actually have a little squared button there. Plus 4x plus 2. And then usually the first time we use a calculator, we'll do push zoom, and we do zoom standard. Once you hit zoom standard the first time, you should never have to push that again, unless you change your window stuff. Okay, so there we go. This is what we're looking for here. So it says to sketch a graph of the function. So let's sketch that. I'm gonna cheat because I can actually take a snip of that, and then I can draw on top of it. So I'm gonna do that. Okay, here's my snip. It's pretty small, but it's okay. It should work well enough. So sketch a graph of the function. Name the relative maximums and minimums. So that's this right here. Hard to see, but that is a relative minimum. And then this one right here is a relative maximum. Okay, so this is all we have to do because it just says sketch the graph and name the relative minimum and maximum. It doesn't say find them. That's a whole different story, but we don't have to worry about that right now. Okay, and then name any x or y intercepts. So here's our, let's find a different color here. So here's our y-intercept, right? And then there's 1, 2, 3 x intercepts. Okay. And then describe our end behavior. Okay, so as x approaches, let's go, we usually start with negative infinity, so as x gets smaller and smaller, what happens to y? So as x is getting smaller and smaller and smaller, look, this graph is going up, so this is going towards positive infinity. And then as x goes to positive infinity, this thing here, y is getting smaller and smaller and smaller, so that means y goes to negative infinity. Okay? Okay, I added one more thing on here. What degree is the function? So this would be a third degree function. That's a function, okay? And if they ever happen to ask, the leading coefficient is 2. We're not asking on there, but leading coefficient, sorry, -2. Okay? Okay, let's take a look at one more example here. Just so you know how to put these into the graphing calculator, we'll do y equals, I'm going to clear this out, and we'll put in this one here, 3x to the third power, arrow over so it comes out of the power, and then plus 2x squared minus 4x minus 3. Okay. Also, if you don't happen to have a graphing calculator, you can always use Desmos as well, and that will help out a lot on this as well. Okay, so here we go. We have that, and now that we've already done our zoom standard, we push graph, and it will slowly, ever so slowly, apparently graph this thing. There it goes. So there's our graph. Okay, I actually made a little bit bigger graph for us, so there's a bigger version of what we have right here. So you can see that's the same thing, so let's just use this. Excuse me, sketch the graph of the function, name relative minimums and maximums. So this here is, let's go back to our blue here, let's see, this here is a relative maximum because it's the highest in this area. Here's our relative minimum because that's the lowest in the area. Name any x or y intercepts. So here's an x-intercept there and an x-intercept there. So these here are the x-intercepts. Here's our y-intercept, right? And then let's see, describe the end behavior. So our end behavior here, as x goes to negative infinity, y goes to, and then we'll also have to figure out what, as x goes to positive infinity, what happens to y then. So we just got to fill in those two blanks. So as x gets smaller and smaller, it ends up going towards negative infinity. And as x gets bigger and bigger, you see it goes up here, that goes towards positive infinity. Okay? And then what degree is the function? This is also a third degree function. Ooh, my pen is having a hard time here. There we go. Third degree function, leading coefficient is 3. Okay? Okay, that's all we have for some attributes of polynomial functions. If you have any further questions, please feel free to ask in class. Thanks.